This presentation describes a topic strictly related to the intelligent manufacturing. In particular, it gives an idea of machine learning-based approaches that can be exploited in order to obtain a holistic design of digital twins. The content of the presentation is shown in the slide. After a brief introduction about the holistic approach and the importance of digital twins, the use of machine learning as good tool to reach the scope is presented. Then, an application related to the off-gas management in the steelworks is presented. Finally, some concluding remarks are provided. In the industrial field, such as in the steelworks, it is fundamental to answer to a significant number of what-if questions in order to know the behavior of a process, of a unit operation, as well as of a utility in particular scenarios. In addition, knowing and considering the consequences of a modification, it is fundamental to make the right choice. In this background, a test bench can be needed and can be virtually provided. The test bench can be called digital twin of the process, the plant or the phenomenon to be analyzed. The digital twin can be used for different purposes. For instance, the forecasting analysis whose results can be used in optimization studies could be a good example. When a digital twin is under development, it is important to take into account that it is often preferable to consider the process from a holistic point of view, because in this way simpler and more accurate models can be obtained. This is possible by following the 3 points reported in the pie chart. The process needs to be considered as a whole, a single entity. The interaction between different components or phenomena can be neglected, and only the aspects which are relevant for a single application or analysis or study need to be considered. By following the holistic approach, several advantages can be obtained, such as less model complexity and computational burden, as well as higher accuracy and efficiency. Indeed, although the detailed approach considers a significant number of details by deepening each single component or sub-process, the holistic approach can address and reproduce the dynamic of a complex non-linear processes avoiding error propagations. This is because its target is only the main objective of the system to be developed. Machine learning can help in the development of holistic models in the terms of black boxes. In this way, phenomena having complex dynamics that are dependent by multiple variables can be reproduced without particular issues. In order to show how the machine learning can be used in the development of holistic digital twins related to the steelworks process, an application related to the off-gas management in integrated steelmaking plant is proposed. In particular, in the framework of the European project GASNET, a library of models was developed in order to forecast the production and the demand of off-gas and of the related energy carriers. For example, they are steam and electricity. These models are fundamental to allow an online optimization of the distribution of the available gases. The model's development started by the selection and the management of data. Then, according to the complexity of the process to be modeled, artificial neural networks were exploited for more complex phenomena, while equation-based models were designed in the case of simpler processes. In the following slides, the most meaningful models are presented. Forecasting the off-gas production by main processes, such as the blast furnace or the basic oxygen furnace processes, is the aim of some developed models. The structure reported in the slide is common between the models and includes a first step of a pre-processing of the input data that are specific or common to some specific trained neural networks. In particular, echo-state neural networks, here simplified as ESN, are here exploited. ESN are a novel concept of recurrent neural networks, whose structure consists of a sparsely connected reservoir layer, which is the only recurrent part of the neural network that exhibits a dynamic behavior, and a readout output layer. ESN approach is characterized by the possibility to draw on a rich set of dynamics generated by the reservoir in order to make regression on a target through supervised algorithms. Unlike other recurrent neural networks, ESN does not use iterative routines that suffer from several numerical issues. For this reason, ESN has low computational training cost and fast convergence. In addition, dynamic reservoir is provided of an auto-feedback nature that allows reflecting traces of the history of the input variables, that anyway are forgot during time with more or less high velocity, according to the echo state property. This last feature can be considered as a sort of short-time memory. The essence features make these neural networks suitable to reproduce the dynamics of steelworks processes. For this reason, they are used to forecast the gas volume flow and the content in carbon monoxide and hydrogen in the 2 hours ahead and with a frequency of 1 minute, in the case of BOF, and of 5 minutes for BF. The choice of specific ESNs allows obtaining higher accuracy and less computational burden. Inputs of the models are a few number of variables that are correlated to the targets and are continuously monitored, registered, and available in the steelworks. They have been selected in order to avoid redundancy or overabundant variables. Among the other inputs, there are the plant unit states that represent the production plan in the form of Boolean values. 1 means that the furnace is in operation, while 0 stands for the switch off of the furnace. The obtained results are then post-processed in order to correct unsuitable values and then are combined in order to obtain the net calorific value of the off gas and its intrinsic heating power. It is evident that no information about the internal phenomena of the process is taken into account from the physical or chemical point of view. Only the real objective is considered in a holistic view of the process. An example of prediction in the case of blast furnace gas production model is shown in this slide. The values in the graphs are normalized for confidentiality reasons, and the forecasting values are compared with the real ones. It is possible to see that the model is able to follow the stationary conditions of the blast furnace operation. In addition, by waiting that the animated figures contains its progress, it is possible to see how the model allows a right prediction of transitory conditions, such as in the case the blast furnace operation is stopped. The high accuracy of the model is also depicted by the graph related to the error defined in the slide. It is less than 6% for the gas volume flow and 7% for the heating value, due to the propagation of some errors, because this last variable is obtained by the combinations of the other of different forecasted variables. Obviously, highest errors correspond to values more ahead in the time. Similar considerations can be done for the more complex prediction of the basic oxygen furnace gas. In this case, the dynamic of the process is more complex, and the model is able to make the following prediction. The quantitative forecasting of recoverable gas volume flow, CO and hydrogen content in the gas, and the qualitative prediction on flammable and total gas. The qualitative behavior of the prediction is due to the accuracy of the available data. The combination of predicted variables gives the net calorific value of the gas and the related heating power. As evident, the model is able to follow the gas production, as also depicted by the graph error that, although higher than the previous presented model, is considered acceptable because the complexity of the process. The current slide shows how a model can be developed in different ways, by exploiting a simpler equation-based approach or through neural networks. This can be done for simple processes, such as the use of blast furnace gas by hot blast stoves. Indeed, the operation of hot blast stoves is regular because of the systematic switching of two main phases: the heating phase, in which the gas combustion is used to heat the stove's walls, and the wind phase, which consists in the heating of cold wind by absorption of the wall heat. Both the developed models allows the prediction every 5 minutes and for the 2 hours ahead of the blast furnace gas demand by hot blast stoves. The equation-based model is here called switch model. It is a simple model that calculates the mean value of used gas in the previous 2 hours by collecting the measurement of real consumed gas. Then, it provides the gas demand for the next 2 hours according to the stove's phase take, provided by the facility, representing the alternation of the heating and wind phases for the next 2 hours. It gives stable values, but the forecasting errors are higher than the neural networks based model, because it is less sensitive to change in operating conditions. The other model is based on ESN. After training step, it is able to forecast the target with a higher accuracy and giving lower errors than the equation-based ones, because it is more adaptable to operating variations. Results of the two models are depicted in this slide, together with the forecasting error. It is evident that ESN-based model is more sensitive to changes, and its error is lower than the switch model in the whole forecasting horizon. A simple neural network was exploited in the development of a model for the prediction of electrical power production by the blast furnace gas expansion turbine. In particular, a feed-forward neural network works in cascade with respect to the ESN-based blast furnace gas forecasting model and to a valve model, to predict the target with high accuracy, as depicted in the figure, and expressed by the very low value of the normal root mean square error. Another ESN-based model has been developed to forecast the steam production by the Linz-Donawitz converters. Few inputs are needed to give a prediction of the target every 1 minute and with a forecasting horizon of 2 hours. The obtained normal root mean square error is low and acceptable. The Rürsal-Heraeus vacuum degassing process consumes steam and electricity, and two models were developed to forecast the future demands. ESNs were exploited in the design, and only the current consumptions and the scheduling of the process were used as inputs. The prediction occurs every 1 minute for the steam and every 15 minutes for the electricity, and the accuracy is good in both the cases, as proved by the reported normal root mean square error. The last model that can be used in the optimization of the off-gas and related energy carriers management is an ESN-based model that allows the forecasting of the electricity demand by the fans used to feed the blow to the blast furnace. The prediction occurs every 15 minutes and for the 2 hours ahead. The model is fed by the inputs that are more correlated to the target. Among them, there is also the values of blast gas volume flow for the next 2 hours, and for this reason, it works in cascade to the model that allows the prediction of these variables. As visible from the animated figure and from the error, the model is able to fulfill this objective. During the presentation, the application of digital twins in the steelworks is presented. This can be included in the intelligent manufacturing theme. Indeed, in the last few years, the need to investigate new scenarios related to project management or to make forecasting analysis to be used in process optimization is become ever more fundamental. This results in improving the industry competitiveness since it is strictly linked to the profitability and sustainability. In this background, the development of virtual plants allowing analyzing the consequences of modification is becoming of primary importance. In addition, often the process to be modeled can be simplified considering it as a single entity, which focuses only on a main objective. This is what can be called the holistic approach. In order to fulfill the previous listed needs, machine learning approaches can be exploited. For this reason, several models have been presented, mostly neural network based, that are useful for the optimization of gas management in integrated steelworks. The presented models were not developed considering all the complex phenomena involved in the modeled process, but they consider it as a whole, as a black box, and only the main objective is reached. In this way, high accuracy and low computational burden is obtained. The obtained results prove the potential that machine learning and the holistic approach can lead inside the steelmaking industries.